In this unit, we're going to talk about some of the basic components of Linux security. So we're going to start by looking at the Linux kernel and the boot process. We'll just talk about that. Then we're going to lead into talking about authentication. We're also going to talk a bit about networks and firewalls with Linux. We'll talk about the Linux firewall IP tables and some of the tools that we have to manage those. And we're also going to look at some of the distributions of Linux, some of the idiosyncrasies with some of the tools that are available to us for security. And then we'll talk about services as well. Not necessarily all in that order. You can see the order down the left-hand side in the menu on the left, which helps you navigate where we are in the lecture each week. So first, let's start by talking about the kernel. So there, usually when we talk about the kernel, there's kind of two parts. There's the monolithic core, and this is the essential required components. So it's essential for the computer to run, right? You cannot start without the core essential components. So that is the monolithic core of the kernel. And then around that you have modules or modular components which are added to the kernel, and this could be things like drivers and so forth, right? And other applications and programs and tools and utilities and so forth and so on. So those are modules. So the important concept here is that that monolithic core is isolated from those modules. So in a perfect world, you shouldn't have, if a module crashes or fails, the kernel should continue running, which is one of the things that contributes to the stability of Linux. When we talk about open source, the kernel is open source. That means that you can download and customize your own kernel. You can download the source code for the kernel and you can make your own version of the Linux kernel if you want. Most of us use what's called a binary kernel. This is a kernel that's already been built and it's distributed with the various distributions of Linux. So it's already been provided for us. We don't have to compile it from source code. So we can just install it and run it, right? It's just part of the operating system, what most of us are typically used to. However, you could download your own version of the kernel. There are custom options for security, so you could download the source code, compile your own version. One of the custom options is to make the kernel a firewall. So it just optimizes the kernel to operate as a firewall. Another one is to configure it for NATing, right? So you can optimize it for configuration for being for NATing, for example, or being a router, right? IP forwarding basically is creating a kernel that's really going to make your Linux machine a router, for example. So lots of different options, but again, most of the time we're going to be using a binary kernel. And in this course, of course, we're using a binary kernel because we installed CentOS 7 from Google. Now, Google may have customized CentOS 7. I don't think they did, but they certainly could have when they created that image for us. But for the most part, to us, it's a binary kernel. So let's talk about the boot process for Linux. When you first start up a machine, there's BIOS or UEFI. UEFI is newer, right? BIOS is pretty old technology at this point. We still talk about it, but you'd be hard pressed to find laptops or servers that still run run BIOS rather. So whether it's BIOS or UEFI, the first thing they're going to do is start the power on self test. And when the power on self test runs, it's going to go out and find a master boot record. Or something like Grub or Lilo that your book talks about. It's going to basically spawn that, which is then going to launch a bootloader, which again is Lilo or Grub, and typically with Linux. Although with Windows, there's other bootloaders, right? There's the NTFS bootloader in Windows, which could actually also load Linux, right? You could set that up to, for it to load Linux from that bootloader. And Grub and Lilo can also load Windows, right? So you can go either way. But the bootloader's job when it starts up is depending on which kernel you want to run, right? You can have multiple kernels, right? It'll ask you which one do you want to start up, the bootloader. And then when you select that, it's going to go out and it's going to find that version of Linux and it's going to start it, right? So it's going to go into that boot directory. It's going to mount that file system, find the VM Linus file, dash version or whatever, and that's actually the kernel that's going to start up. The first thing the kernel is going to do when the kernel starts up, it starts a process called init. So init is the very first process that gets started, and from init, so init's first job is it's going to check to see what run level it's at. So it starts up and it says, what run level am I? I'm going to talk more about run levels here in just a second, but it's going to ask you what run level am I, and depending on the run level, it's going to figure out what services or processes do I need to start or stop. So when init starts, it could be replacing another init that was at a different run level. So you could say, okay, I'm changing to a different run level, so I have to start some stuff and kill some other stuff that shouldn't be running at this run level. And you'll see what that means here in a second. So it's going to check all that stuff, and that's going to tell it which daemons or which processes and services it needs to run. One of those processes is going to be the login process. That's what allows you to log in, right? So until that process starts, you won't be able to log into your Linux server. When you log in, the first thing it's going to do is start bash, and then from bash you can launch your own processes in your own user space. So when you do the lab, you're going to see this. When you go in the lab and you run the ps command, you're going to see that in your user space, the bash command is running, and then as well as other processes like the ps command itself will be listed there, right? So you'll see that when you do the lab. So when we talk about Linux processes, lots of different words we use, lots of different vernacular just to define these. Program is just an executable file. It's a binary file that can be run and basically runs as a process at some point. You can execute that, right? A process is a program that is running either in memory or in the CPU, right? So it's in memory and running on the CPU. So it's a program in action, basically, right? So a program, when you execute it, becomes a process. A user process is when you run a process. You're logged in and you start something, which is a process that's going to be running, right? A daemon process is a process that is not associated with the user space. So it's running in the system space as opposed to the user space. And you'll see that in the lab when you run the ps command. You'll see certain things are running in the user space, and these are typically services, right? And you're going to see how to work with services in the lab. And then the process ID is, so every single process that's running on your system is going to have its own unique process ID, and you're going to use that to control the process, to kill it, to halt it, what have you. And then finally, a child process. So when a process starts, it has a child. Children typically have a parent. The only process that does not have a parent is init, right? Because init is, the first process that gets started, so it doesn't have a parent. Although I guess arguably you could say that the kernel is its parent, but it gets a little bit dicey when we start to talk about that, right? So just as an example, you might look with the ps command and see process number 1 spawn process number 2 and 3, process 2 launched process 4 and process 5, right? And each one of them has a process ID and references its parent process ID. That's what the PPID is. This is parent process ID. So any process that you see with the ps command, you should be able to trace it to its parent, and then you can trace that to its parent and that to its parent until you get all the way back up to the init process. Init is almost always process number 1. So when you look in Linux, process 1 is typically going to be init, and then systemd might be the next process, and so forth and so on. And here's another example, right? Init at the top of the tree. So as an example, in the lab, you're going to type the ps command. That's going to show you processes that are running. In my case, since I'm logged in with SU, you see SU. I'm using bash, so that's running in my user space, and I ran the ps command so we can see that. If you run it with the -f command, it's going to give you a little bit more information. It's going to give you the process ID and the parent process ID in addition to some other things, right? So you get a little bit more information with these switches. If you use the EF command, it's going to give you even more stuff. And the PSAX command uses the system5 formatting for the ps command, which just looks a little bit different. But ps-l is probably one of the more useful, which has a lot more information. For example, you're going to see the state of the process. You'll see its process ID, its parent's ID. You'll see the priority with which it's running, which is an integer between 0 and 127. Obviously, 127 is the highest priority. There's a nice, so nice basically means, can that process take over, how important is that process? I'll show you what that means in just a second. And then you also have the name of the process on the right, which is behind me, right? You can't see it because I'm in the way. So the top command is kind of useful. If you want to see what processes are currently running, you can run and how much CPU and RAM they're using. Run the top command, and it's going to show you the %CPU, %memory. You can kind of get a sense of which processes. And this command, when you run it, it's going to run in real time and constantly tell you what different processes are using. It's like the process manager in Windows, for example, right? Where you can see kind of in real time what's happening. Doesn't give you like a nice graph in the command line, right? You have to use the GUI to do all that, or you can use third-party utilities that you connect to your Linux machine, and you can look at that type of information. But this is usually good enough for a system administrator. One of the cool things in here, and you can't do this in Windows, right? When you're in the command prompt, is you can use the the K command to just kill a process. So if you see something in here that's rogue, hit K, type in the process ID, it'll try to kill it, right? You can do it right from here without having to exit from the command. Use the Q key to exit from this command when it's running in real time. So if you do need to kill a process, you'll need to know its process ID or the name of the process. You can also do it with the name, but I'm just going to show you here how to do it with the kill command. So when you run the kill command, you just type kill, the process ID, and it'll try to kill it, but you can also pass a specific kill signal. Kill-L will show you all the different kill signals that are available. They are kill signal 1, which is a hang up, 2, which is interrupt, 3, which is quit, same as hitting control, reverse solidus. You have a sig term, sig kill. Pretty much all of these can be trapped by a process. So when somebody writes software, they can have it trap these different kill signals. So for example, you don't want programs to just die out of nowhere, right? So as a programmer, you could have it capture the, say the sig quit, right? So you can have it capture the quit signal, and then it knows, okay, somebody wants me to quit, so let me clean up everything I'm doing and then quit, right? But a sig 9 or sig kill, which is signal 9, that one you cannot put a trap in, right? It's just going to kill no matter what you do, right? So you can't trap those. And that's how we kill a process that's going rogue, right? It's running and we can't stop it, right? We're going to use sig kill. Obviously, we want to try the other ones first, and if they don't work, we can go nuclear and go right to the sig kill. By default, the command will always do a 9 if you don't give it an option in the command. So to kill a process, first we have to get the process ID by running the PS command. Once we have the process ID, we could tell it, send it the, which interrupt we want to send it, and then the process ID. So here we're doing a -3 to send it the third one that you saw on my list before, and then you have the process ID, and it's going to try to kill that, and that's it. We can also just pass the name of that process. So for example, if I want to kill bash, I can just type bash, and it'll try to kill bash. So that works as well. Process priority. So, the time slice or the priority that a process has is basically an integer between 0 and 127, right? That's how much priority the system is going to give it. But you can also be nice. And what that means is you can tell the system when you're running a process that it can deprioritize. It can lower the priority of your process. You can tell the system with the nice command, hey, I'm running something, but it's not that important. So if somebody else needs the processor, go ahead and set me aside and let somebody else use it. And then when you're not busy, you can run me again, right? And basically that's going to be a value that is going to be between -20 and +20. The more positive your nice number, the nicer you are, right? So when you start at 0, the closer you get to 20, the nicer you are. 20 is the nicest you can possibly be. A negative number means that you're not being nice, right? That means you're being mean, right? So the meaner you are, the more you're telling the system you want to prioritize your process. Only root can give you a negative nice. Only root can make you mean, right? So you, by default, as a regular user, you can only be nice. You can't be mean, but you can. But the root can go in and change the priority of your process to make it a little bit more mean and kind of take more of that processing time. That's how you can set a priority of your process higher by using the, a negative number. And renice is the command that you use to change the nice, the nice factor for your process. All right, so daemons and services, just kind of revisit this a little bit. If you go and look in your Linux machine, you're going to see an etc directory. Right inside etc, there's etc rc.d. This is the old POSIX compliant standard way of indicating, what you want started and stopped at different run levels. Now, in the real world with CentOS, there's another process called systemd that runs under init. So under init, you've got one of the first things that starts is systemd, which is a service manager. That's a little bit different than this basic model that I'm going to show you here, but it's important to understand this because every Linux system in the world will support this option. It may not necessarily be used by default when you install things with a package manager and so forth, and you'll see what that looks like here in a bit. So with the So under etc rc.d, you're going to see a whole bunch of files. But if you, so for example, each one of those files is going to be essentially a batch script, or a bash script rather, not batch, that starts or stops that file. But what you do is you call that script with a start, either with start or with stop, right? And depending on whether it's set to start or stop at run levels, it'll start it or stop it. I'll show you how that's set here in just a second. So this is just a basic example of a starter, a script that can start and stop a process. So what you do is, so basically it's this simple, right? You have an executable file somewhere on the system, doesn't matter where it is, but you go into ours. Let's say you want that to run whenever somebody's at run level 3. You go into rc3.d, and which is a directory. You create a file. If it starts with an S, it means start. If it starts with a K, it means to stop it, K for kill, right? Then you give it an integer, which has to be, unique. It can't be, somebody can't already be using that integer. That's the priority, right? So the lower the integer, that's, the first one's going to get stopped or started. And then you give it a name. And inside that file, you indicate instructions what to do for start and stop, and it's really that simple. That's how you install a service in Linux, right? It's pretty straightforward. It's very elegant how it works, really. So as an example, if you look in etc rc.d, you're going to see these different files, the rc0, 1, 2, 3, and so forth and so on. What are these different run levels? Run level 0 means turn the machine off. Run level 1 is single user mode. Run level 2 is multi-user mode with networking, but no network services, right? Sorry, I got a typo there. It should be just no networking. 3 is full multi-user with networking, so 2 is multi-user, no networking. 3 is with networking. 5 is multi-user networking with X Windows, right, which is the desktop, which of course we don't have. And then run level 6 is reboot. When you configure your Linux server, you're going to tell it what is your default run level, meaning when somebody turns on the server, which run level do you go to by default? If you're running a Linux machine with a desktop, it'll be 5, and if you're running one like in our Google environment that has no desktop, it'll be 3, right? It wouldn't be 5. Now, that's not to say that you couldn't use 5 anyway in Google and just set desktop to not start, right? Theoretically, you can do that, so you can have, more granular controls of your run levels, right? But that's not typical. Most people don't do that. If you really want to be mean, you can set the default run level to 6. Then every time your machine starts up, it's going to go to run level 6, which tells it to restart. And when it comes back up, it's going to go to 6, which is going to restart, and over and over and over again, right? So you could do that if you want to mess somebody, I guess. All right, so back to this little diagram here. I'll get you back to where we were before. So how does this work? If you go and look in the directory like rc1.d, run level 1, which is pretty basic, right? This is what you're going to see. You're going to see a whole bunch of soft links that go to a file in init.d, which is that bash script that I showed you earlier, which can start or stop that particular service. So you can see here, if you go to run level 1, it's going to kill NFS, but it's going to start random, firewall, network, NFS, and so forth. I'm sorry, run level 3. So when you go to run level 3, this is all the stuff that's going to get either stopped or started. And again, pretty straightforward. Now, when you do the lab, it's going to look a little bit different. You're going to see this on your lab system, and you can go and look at this, and you can, see what it looks like, and you can see exactly what I'm showing you here. But you're only going to see very few services are going to be in there. But one service that you should see is system.d, and that is kind of the wrapper that handles all of the services that we install in our CentOS system. So it uses the system daemon or systemd. So it's just a different daemon that manages all these services. It has more control over our services. It's just a little bit different. So it's not this default mechanism. But in any POSIX compliant Linux system, you're going to have this option. This will work on almost every system. It's just not commonly used, but you can make your own service and configure it to run using this mechanism if you wanted to. Although generally with the package manager, they want you to use systemd. So if you use the check config command, this is basically how you would try to see what services are set to start and stop at different run levels. And you can also use the check config command to change the behavior of services. So instead of going into the text files, or no, going into the links rather, the soft links, and changing the S to a K, you could do it here and it'll manage it all for you. So here you can see that I'm showing SSHD, what its run levels are. If we set SSHD to on, it'll just turn it on at all run levels. We can set it on just at run level 3 and 5. That's what 35 means, 3 and 5. They only go up to 6, so you don't need to worry about, you know, which integer is which, right? You can just put them all together. But that would set SSHD to only run at run level 3 and 5. Again, you're not going to see SSHD in yours in RC on that CentOS system we use for the labs, because we're using system D instead, right? So you'll see it in there when you do the lab. It's going to look a little different. All right, so authentication. By default, Linux is going to use its local database, which is the shadow database, right? So basically you have a password file or the PASSWD file in Etsy with a list of all the user accounts. The shadow file is where their account name and their password is. The password file is generally available for anybody to look at in case they want to see who all the users are, but you can't see the hash for the password. You have to go to the shadow file to do that. And then there's also a group file, right? So you can see all the different groups on the system as well. And that's basically how Linux manages user account. Again, it's another very elegantly simple way to manage user accounts, right? It's a lot simpler than, you know, some other operating systems out there that will go unnamed in this course. There are other authentication databases. For example, LDAP. You could use LDAP, which is Lightweight Directory Access Protocol, right? This is kind of like Active Directory. In fact, Active Directory supports LDAP, which makes Linux compatible with Active Directory. I ask you about that in the discussion threads. Active Directory could be used. So your Linux machine could actually be part of an Active Directory domain. This is something that's implemented with the Samba packages in Linux. NIS, which is an old Oracle. This is part of NSF, or the net, you know. But you could use NIS, or Network Information System, right, which is the Oracle standard. This is used to be called Yellow Pages, right? And it's basically, it's actually also elegantly simple. All NIS really does is it creates a master password and shadow file and group file on a master server, and then it uses the distributed network file system to, that should be NFS, not NSF, sorry, typo, but it uses network file system to share those across all the different servers, you know, the different servers that are the multiple heads, right? Kind of like Active Directory in Windows is the same concept as far as being, you know, a distributed database. But when a user goes to log in, you don't go to your local password and shadow file. Instead, it goes to the one configured in the network. It interrogates the network and says, okay, who's got a password and shadow file I can access with NFS, and it's going to come back and say, here's the server you can go to, and the mechanism basically works the same from there. So again, elegantly simple, but also there's complex options like Active Directory. In the real world, I think a lot of Linux systems in corporate environments and so forth are typically going to use LDAP or Active Directory because we want single sign-on, right? We don't want to have to manage user accounts on all of our servers. And the problem with NIS is that it only works with Linux. So it's not compatible with Windows, which means now I have two different environments with user accounts. So the more common approach is to use LDAP or Active Directory. So let's talk about firewalls a little bit. But before I talk about firewalls, I'm going to give you kind of a brief overview. If you need a refresher on TCP and how TCP protocol and IP addresses and all that stuff, I've got a different lecture you can look at, which I'll post for you. But you can go to my YouTube channel, and there's another lecture that's kind of a networking 101 to give you a nice refresher. But just to kind of talk what we need to in this course, the three layers of the OSI model that we care about, and I hate to talk about the OSI model, but that's what our textbook talks about. Every textbook uses OSI, but really TCP is the real model, right? But the three layers that we care about in TCP, I'll say TCP and not OSI, are the data link, network, and transport layer. At the data link layer, to make decisions about what we can do with traffic on a network, we can look at the MAC address and the protocols at the data link layer. We can look at the network layer at the source IP address, destination IP address, and the protocol version, IPv4 or IPv6, right? Those are the only two. And then at the transport layer, we have source port, destination port, the flags. And basically, we talk about the flags. It's, you know, what kind of packet is it trying to establish a connection, close a connection, and so forth.
And that can tell us what the connection state is. The connection state can derive from things like sequence numbers and the acknowledgement numbers in the segment header, right? So you have a segment, then you have a packet, then you have a frame at the data link layer. So we look at these various headers in these different layers of the TCP model, and we can determine certain things and make decisions about those datagrams as they traverse through a network. So most commonly, we might look at something like the destination port and destination IP address. So as a very simple example, we might say allow all TCP traffic on port 80 going to a specific IP address. And then we might want to block everything on port 25 from getting to the internet if we're setting up a firewall. This is some basic rules. And we would make a series of rules out of these different parameters that we're going to look at and try to think about how we want to handle that traffic. So rules can generally evaluate any combination of information found in all of those headers I talked about. Again, a segment header, the packet header, or the frame header at the data link layer. The target and source addresses are typically used, the connection state. You can even look at the payload with things like proxy servers and application level firewalls. We're not going to talk about that too much in this class because Linux natively doesn't really do that stuff, but you can add packages to do that, which is a whole nother topic, right? Generally, there are two types of firewalls. There are what we call stateless firewalls and stateful firewalls. A stateless firewall only applies rules to one packet at a time as it traverses through the firewall. The sequence of the packet is not considered. The state is not considered. For example, you might say that only certain MAC addresses are allowed through, right? But there's no concept of state of MAC addresses, right? A stateful rule, on the other hand, is one that looks at and considers the state of a connection and determines if return traffic is associated with that connection, right? So, for example, you try to access a web page from behind your firewall, it allows the response to come back to the firewall. But if somebody tries to open a new connection into your network, it blocks it, right? Stateful firewalls, as a rule, require more resources. So generally, when we work with firewalls, we create stateless rules to be processed first because they will drop packets that we know we don't want. Then we get into the stateful rules. So anything that makes it to stateless will then use the resources of stateful rules. When I think about the difference between these two, I think about the difference between a traffic cop and a detective, right? A police officer on the street is directing traffic. They only care about the cars that are in front of them, right? It's very, in the moment, ephemeral. They're looking at a vehicle, making a decision as to which way that car needs to go. Whereas the detective doesn't typically do that. They're playing the long game. They're investigating a crime over, a longer period of time, right? So a traffic cop can have an effect on many more cars, and it doesn't ruin his day, right? They can direct 20,000 cars through an intersection, and that could be routine. But a detective can't be working on 20,000 cases. It would take too many resources, right? So we want to filter things down with stateless rules, and then with the stateful, we can do other things that are more intelligent with those packets. And this might handle things like denial of service attacks could be dropped at stateless level before they make it to that stateful level, for example. All right, so when we talk about different types of rules, there's two categories of firewalls, in my opinion. The first category is Unix, Linux, and BSD, and they pretty much all work the same way. They all use some variation of the IP tables libraries, right? So the kernel, a core component of the kernel, whether it's Unix, BSD, or Linux, is IP tables, which is a native firewall in every kernel in Linux, right? Well, almost every. So IP tables and chains are what we use to do that. There's also Cisco. Cisco is a proprietary technology. Under the hood, does it use IP tables? Maybe. I think most people believe that they're using some form of BSD in Cisco devices, so who knows? But it's all proprietary. We have no access to it. But almost every other firewall in the world is using Unix, Linux, or BSD. Out of the box, they're using IP tables. We'll talk about that here in a second. But when we look at Cisco firewall rules, they're really relatively simple, right? You have a list number, and then you have the rule which is going to permit or deny, and then the IP address, the source, whether it's IP or ICMP, the source IP, the source mask, the target IP, the target mask. If you forget about subnet masking or masking, go look at my other lectures. I don't want to waste too much time in this lecture talking about it, but you can also have a port. This is just a very basic rule. Almost every Cisco router and firewall can support a rule like this. Firewalls have more options, but this is just a basic example. And the access lists are how you group these rules. So for example, access list 101, I'm going to permit TCP traffic from anywhere going to my web server on port 80. And then I'm going to deny all traffic coming from anywhere to that server, right? So first it's going to say, are you trying to talk to me on port 80? I'm going to let you through. You're not on port 80, you're getting dropped, right? So everything else gets dropped. And you might have some additional rules like allowing blocking port 25 or something like that, or 443 and so forth and so on. And you might have other access lists, and you're going to apply each one of those access lists to some interface, right? Inbound or outbound each interface. That's basically how this works, right? It's relatively straightforward. IP tables is a little more complicated, right? Although we can simplify that, and I'm going to show you how to do that in the lab, but basically traffic's going to come into the network interface card, and it's going to go to the pre-routing processor. That's going to send it to the IP processor, which is going to evaluate that data. So IP is going to evaluate the packet and say, is this a packet that's going to me, or is this a packet that's just going through me to someone else? If it's going through me and going to somewhere else, that goes to a forwarding chain. So forwarding chain basically evaluates that packet at the segment and the packet level, and even the data link level, make a decision, and then send it to post-processing, and off it goes to wherever it needs to go. This is how Linux works as a router or a firewall. It's going to go through that forwarding chain. Now, some traffic is destined for me, right? It's coming into the Linux machine itself. Maybe it's a request to a web server running on the Linux server, or to a FTP server, SSH, or whatever, right? Some service running on that server. So in those cases, the packet is directed to an input chain. The input chain then decides, do I allow this traffic to go to a process, or do I not allow it and drop the packet, right? One or the other could happen. If it goes to a process, the process will then, a process either could generate new traffic or respond to something else, but in other cases, it's going to go to a routing chain, which then goes to the output chain to decide whether or not it's allowed out of the machine, and then off it goes to post routing and out to wherever it needs to go. So primarily what we are going to work with in our firewalls in Linux is going to be either a forwarding chain, which is all the traffic that's going through our Linux machine but isn't destined for the machine itself, and then the input, so that's a forward chain, and then the input chain, which is traffic coming into our machine for a process, and then the output, which is stuff leaving our machine going somewhere else. What's interesting about this is when you looked at Cisco, there really was no concept of input and output, because they're almost never the final destination for a packet. They're always going through that machine, so it's not really a concern. In Linux, however, we use Linux both ways. Linux machines can be a firewall and a router, in which case they're mostly going to be forwarding chains that we configure, or a Linux machine is a server, in which case the input and output chains are going to be more important to us. So depending on how we implement it, one of these, but it can do all of it, right? So it's a very effective host firewall with the input and output chains, and it's also a very capable network firewall with forwarding chains. So the Linux firewall, if you want to look at IP tables in your machine in the lab, I'm going to have you run the IP tables command, and it'll allow up a bunch of stuff so you can see what your IP tables configuration looks like. Now, we're not in the lab going to actually configure IP tables. Instead, we're going to do something like this. We're going to run IP tables, and we're going to take a look at it, but we're not actually going to edit IP tables. We're going to use Firewall D, which is a service that layers on top of IP tables. And use actually a graphical user interface if you have the desktop to manage Firewall D, which thus manages IP tables. So it abstracts us from having to actually manage IP tables. Now that said, you can remove Firewall D from a Linux machine like a CentOS installation, and you could implement your firewall rules all in IP tables and do it the old-fashioned way. And you get very granular control in IP tables. I teach a whole class on how to use IP tables. So I do a whole network security course where we learn about IP tables and how to manage IP tables and how to set up our firewall rules and so forth. But in this class, we're going to use Firewall D. It's a lot easier. It extracts all that complicated stuff rather than IP tables. And it's really just as effective for the most part. But I would argue that if you go out and you buy a commercial firewall like Barracuda F5, pretty much everything but Cisco, almost all of them are using IP tables under the hood. So they're all running some kernel like BSD or Linux They're all using some variation of IP tables, almost all of them, and you're managing it with something like Firewall D, right? That's their proprietary software that layers on top of IP tables, so you don't have to mess around. But it's kind of interesting. In theory, could you go into one of those firewalls, get root access, and look at IP tables? Sure. I've done it in my Barracuda firewalls. I'll go in and just for the heck of it, I'll run the IP tables command to see what it looks like, right? But it's all managed by their proprietary interface. So as far as network encryption goes, number one, always use SSH. Your book talks about that. Generally, we want to shut down services that do not use encryption. Almost every service available in Linux is going to include a version of their network communication that supports SSL or TLS. So almost everything, for example, HTTPD has support for TLS or SSL. MySQL, you can turn on SSL. Which is a database engine. You can use SSL with email. You can use it with Samba. LDAP has a secure version of it, right? So when we're looking at all the different services we have on our machine, we want to try to use variations of configurations in those services that use the encrypted versions of that traffic, and we're going to see some of that later on in the course. As far as updates go, obviously we can use the package manager to do our updates in Linux to manage those updates. That's great for home users. It does automatic updates. You configure it that way, but for commercial users, for system administrators, generally we're going to want to review and test updates to make sure that they don't have negative effects on our server before we apply those updates. But it's a sort of a balancing act, because you don't want to wait too long before you put updates, because when you have those zero-day vulnerabilities, you want to get those patched as soon as possible. But again, at the same time, you also don't want to impact the services on your network. Sometimes when you apply patches, it can fix a security hole that somebody was actually using for legitimate reasons, right? So we have to be very careful with those types of things. But there are some automated update management that takes into account, so you can test your updates and then automate the delivery of those updates to your entire fleet of Linux servers, or Unix and BSD even. And as far as virtualization goes in security, again, this is one of those topics, tip of the iceberg here. I actually teach an entire class about virtualization and cloud computing security. So virtualization security and cloud computing security, it's a 400 level class at one of the universities I teach at. But basically, the only three types of virtualization you really need to know about in this class are bare metal virtualization, which is what we call a type 1 hypervisor, which is a hypervisor that is the operating system. In other words, the virtualization software is the operating system itself. It's the most efficient way to do virtualization. And then layered on top of that, you have hardware-assisted virtualization. This is where the hypervisor can use certain features within the CPU. Both AMD and Intel include features that enable more efficient virtualization. It's features that have been added over the last 10 years or so. And then you have para-virtualization and then platform-level virtual machines, which is arguably these type 2 hypervisors, where your hypervisor, rather than being an operating system, is an application running within the operating system. So you have an operating system, within that an application, which is then allowing you to run other operating systems within it with more applications, right? As you can kind of guess that that's not as efficient as a bare metal hypervisor, because there's more layers there, right? Before we get to the processor. So again, these aren't as efficient, but there's certainly a time and a place to use those. We used to use them a lot in classes like this, right? But now we're using type 1 hypervisor, because our virtual machines in Google are most likely a type 1 hypervisor, so they can run much more efficiently. And the last layer is application virtualization. This is something that's not really common yet in our college classes, but you might hear of Kubernetes, or basically these containerization, right? Application containerization, so you can run your apps in containers. Definitely a very secure way to deploy apps in shared environments. It's a little more efficient than full-on virtualization. So one of the problems with virtualization is, all of us are running our own machines, which requires overhead. But what if we all just have our own applications and they can all run on the same platform? That's where containerization comes in. It's a little more efficient, but there's, the jury's still out on security of that when we're all swimming in the same virtual environments. There are certainly security concerns with virtualization. They're a little bit beyond the discussion in this course, but it's important to understand virtualization to the level that we know these different types of hypervisors and how Linux machines might be run in a real-world environment. Now, as far as the distributions of Linux go, as far as, why do we care about those in this lecture? Because different distributions have different tools and utilities that are available to us and what they implement. So, for example, Red Hat and Canonical, both of them include Apache, both of them use BSFTP, both of them have GNOME for the desktop, although you can use other desktops if you like. Some distros underneath Canonical, use KDE or something like that, and they both have some variation of cups. And that stuff you can pretty much expect in most of the distributions. But take a look at this chart. This is a list of all the different functions and the different packages that are available in different distributions. So, for example, for DNS, some distributions might use Bind, others are using Daniel J. Bernstein's DNS, right? For file transfer, some are using ProFTP, some are using VSFTP, and so forth, right? For printing, some are using CUP, some are using System 5, some are using Line Printer Next Generation or LPRNG, right? For mail, they're using different packages, right? Some systems use Exim, some are using QMail. So just different packages. This is important because you have to be aware of the things we learn about CentOS. They may be different in other distros. They might be slightly different tools when we look at things in CentOS. You go and look at something in Ubuntu or a Debian-based package, it might be completely different. So there is a lot of variation in these distributions. So you might learn how to secure VSFTP, for example, in this class. We're going to look at that, but you might get out in the real world and they're using ProFTP, so you have to know how to manage that package as well. So a lot of variation is something we don't have with Windows, right? Windows doesn't have a lot of variation. If you're running a web server, 99% of the time it's Internet Information Services in Windows, right? But in Linux, there are other variations, right? Even versions and types of Apache and so forth, right? So in summary, what we talked about the Linux kernel, we talked about the boot process, I talked about processes, daemons, and services, a little bit about how they work and how to manage those. We discussed authentication. We probably spent the most time talking about network security, and in the lab do a lot of network security stuff in this unit. We're going to talk about some of that later on in the course as well. We talked about updates, virtualization, and I finally ended by talking about some of the variations and distributions. If you have any questions, let me know, and thanks for watching.